Unit 1 was all about quadratics, change in tandem, all of your concavity, and then rational functions. Now again, we cannot forget those things because of this being an AP class. We got to keep bringing those back. However, Unit 2 is going to jump into two other types of functions eventually, not today. We're going to be focusing on exponentials and logarithms in Unit 2. Both of them you've done before, you've studied before in Algebra 2, but I know for some of us it's been a minute. We're going to start, though, in kind of like a transition period from what we did before to now, and we're going to talk about sequences. So a sequence is a function from the whole numbers to the real numbers. Normally, functions go from real to real, but since we're going from the whole numbers to the real numbers, that means that we can only plug in whole numbers. Like 0, 1, 2, 3, 4, 5. Notice there's no negatives. Notice there's no fractions. There's no decimals. Just the whole numbers. But when we plug them into the sequence, we could get any real number, any fraction, any negative number, any whole number. Doesn't matter. As a result, when we graph sequences, they look like discrete points on a graph because we'll have coordinate points, but we don't have the connecting pieces between them because they're discrete. We can only use the whole number answers. So easy enough. Sequences are just like patterns, and patterns are just like functions. Consider the sequence defined by, we pronounce this a sub n. Have you all ever seen sequences before? I honestly can't remember if it's been in curriculum before. Yes, we have. Okay. A sub n is equal to 4n minus 3. In this kind of thing, a sequence doesn't really use x's and y's. It uses n's and a sub n's, or s sub n's. It's telling you the number in the pattern and then the output, or the term. So this is telling us we can find any term in the sequence by taking 4 times the number of the term it is minus 3. If we want to find a sub 1 and a sub 7, this is just telling me to use 1 as the n value. 4 times 1 minus 3 is what? That's 4 minus 3. So a sub 1 is equal to 1. So it works just like a function where you take numbers, you plug them in. We're just only ever going to be plugging in whole numbers. So if we wanted a sub 7, that means that the number in the pattern that I'm looking for is the 7th number in the pattern. That would be 28 minus 3, so a sub 7 is equal to 25. The 7th term in the sequence is 25. Do we see that notation and how that works? Okay. Now there are two types of sequences we're going to study in this class, arithmetic and geometric sequences. This totally looks like the word arithmetic. I agree with you, but when we're talking about sequences, we pronounce that arithmetic. So say that to yourself once, arithmetic. Yeah, just a little bit different than arithmetic. So it's arithmetic and geometric sequences. Again, you've probably seen these before, but it's been a minute. For arithmetic sequences have a common difference or a constant rate of change. What other types of functions do we have that have a constant rate of change? I think I heard somebody say it. Linear. Yeah, linear equations have a constant rate of change. So linear functions do have constant rates of change. So these kinds of sequences, arithmetic sequences, will have a common difference. We can think sort of a common difference being like a slope. It is not a slope because it is not a linear function, but we can think of it as the constant change between all of my terms. There are two versions of an equation that are formulas for the sequences we will see. This is a sub n equal to a sub 0 plus the common difference times n. That is going to be like your slope-intercept form. It's like the most simplified version of a sequence we can have. The second kind, and probably the one we will use the most because it requires you not to have the initial value, it's a sub n equal to a sub k plus d, it's common difference, times n minus k. Now again, you're like, what the world? This is just point slope form. Y minus y1 equal to m times x minus x1. We've switched the letters from an equation with x's and y's to a sequence with a sub n and a sub k. Those are your y1, y2. Okay, so it's not anything new. We're just changing the formulas a little bit. But let's detail ourselves here. A sub 0 is your initial value. Just the same way that the b in y equals mx plus b is your initial value or your y-intercept. D is your common difference, just like slope. The D is on all the places that the m would be. And a sub k is called your kth term of the sequence, meaning that is the y2, the other output. Now we've kind of already discussed this. Arithmetic sequences behave like linear functions, except they're not continuous. Remember, we cannot connect them together. They're just going to be little dots. Increasing arithmetic sequences increase equally each step, just the same way that slope stays the same. So let's graph our first arithmetic sequence. We have a sub n equal to 3n plus 1. Just like with a function, we're going to want to have a table of inputs and outputs. But instead of x's and y's, we're going to use n and a sub n. Because these functions start with the whole numbers, you're not going to start at like -3 and -5. You're always going to start at 0. We can't use negative numbers with sequences because those are not whole numbers. Whole numbers are just the positive ones. Okay, so that means we're doing 3 times 0 plus 1, which beep, beep, beep. What is 3 times 0 plus 1? 1. So we have our first point in our sequence, 0, 1. Boom. Now again, because we're only using whole numbers, we're not going to plug in like a half. We're going to plug in the next whole number, a 1. 3 times 1 plus 1, that's 4. We plug in 2. 3 times 2 plus 1, that's 7. We plug in 3. 3 times 3 plus 1, that's 10. What do you notice about all of these outputs? Or the change in these outputs? What's happening every time? Well, true, they are odd even, but what's the difference between them? 3. Our common difference is 3. It's literally just like a linear equation. We'll go ahead and plot these points, and I know it goes off screen, so we have 1, 4, 2, 7, and then 3, 10 is already off screen. Resist the urge to play connect the dots. These do not get connected. They are sequences. So they are discrete. We will never connect them together. Okay, again, we determine whether something is arithmetic and eventually geometric by the change in the outputs. You already noticed this, but these each time are going up by 3. A consistent rate of change, meaning it has a common difference. That is how we're going to be able to determine if a sequence is arithmetic and eventually geometric when I teach you that pattern. Questions, comments, concerns? Okay. So for part A of example 2, we're just trying to determine if the sequence could be arithmetic, and if it is, we'll find that common difference. The way that we do this, again, is just by creating a table of n and a sub n, or s sub n in this case. What number do we start with for sequences? 0. Cool. If we plug 0 in there, and we can do this part in our brain, we don't need to show our work. What's 0 squared minus 3? There it is. And then if I plug in 1, what's 1 squared minus 3? 1 squared is 1, so 1 minus 3, negative 2. Okay, if we plug in 2, 1. If we plug in 3, 6. 3 squared is 9. 9 minus 3 is 6. Okay, we look at these outputs. What is the change in the outputs here? Between negative 3 and 2, we'd have to add 1. Check. Between negative 2 and 1, what's the change? Plus 3. Between 1 and 6, what's the change? Plus 5. Were all of those numbers the same in my changes? So this is not an arithmetic sequence. We have to have a common difference or a constant rate of change, so we would just say this one is not arithmetic. And arithmetic is a long word. I'm okay if you shorten it to this. Not arithmetic. I think that's enough information for us to try B, C, and D all on our own. C and D don't give you the formula, they just give you the outputs, so it's actually an easier question. I want to see if we can handle that one on our own. That should have been enough time, hopefully, to get started. We're either stuck or we got it, so let's talk about it. For the equation in part B, again, we want to plug in some values to get out some values, the same way we've always done inputs and outputs, but with Sequences, we only use whole numbers. So I'm going to use 0, 1, 2, and 3. Obviously, you could keep going if you wanted more information, but for me, that's enough to pretty much see a pattern. This is 6 minus 2 times 0. 6 minus 2 times 0 is 6 minus 0, which is 6. This is 6 minus 2 times 1. Well, 6 minus 2 times 1, which is 6 minus 2, that's 4. 6 minus 2 times 2, well, 2 times 2 is 4, so 6 minus 4 is 2. And 6 minus 2 times 3 is 6 minus 6, which is 0. What do we notice about the pattern of these outputs? It subtracts 2 every time. Since that number is all the same, then we have an arithmetic sequence, and the common difference is that -2 number. The way in which it's changing, the pattern, is subtracting 2. Now this makes a lot of sense to me, because first of all, we said arithmetic sequences are like linear equations, yeah? Which one of these is linear? A or B, if this was an equation? Can this one be linear if it has a square? No, that's a quadratic. This one looks like a linear equation, yeah? And right next to the x, which I know is an n, what number do you see? Oh, snap, -2. That's our common difference. Okay, for C and D, they actually needed way less work. Since you already have the sequence written out, notice the sequence doesn't end, we have the ... at the side. We just needed to figure out the change in these outputs. From -7 to -2, we had to add 5. From -2 to 3, we had to add 5. 3 to 8, 5 more. 8 to 13, 5 more. So if that change in the outputs or in the sequence is consistent, that is an arithmetic sequence. And in this case, the common difference would be 5, because that's the number that changed it every time. Now for D, if I go look at that one, this is -3, and then we go +5, and then we go -7, and we go +9. There is a nice pattern to it. We're adding a different odd number every time, change the sign, but it is not an arithmetic pattern, so we would say it is not arithmetic. How'd we do? Okay, cool. Guess I should box my answers. So let's make it a little bit more complicated here. Example 3 says, let a sub n be an arithmetic sequence with a sub 3 equal to 8 and d equal to -3. First, find an expression for a sub n and use the expression to find a sub 12. Okay, here's what I know. I know that if I'm normally given a point and a slope with a linear equation, I use point-slope form. So the form of an equation we're going to want to use here and use the most is this version. And we're going to write it at the top of our paper since it's on the other side of the paper, and that's just annoying to flip back and forth all the time. A sub n equal to a sub k plus d times n minus k is your point-slope version of a sequence. Since we weren't given the initial value, we can't use the initial value version. We use the version just like this. We fill in what we know. Here's what we know. We know that the sequence can be written if you have an output, let's say it's a sub 3, plus a common difference, which is -3, times the number minus that term. Okay, let's make sure we understand where I got all these things from. I should probably color code. Here's a sub 3, and here's 3. And here's my -3. Do we see where everything came from? We used the example point, air quotes point, that they gave us of a sub 3 equal to 8 in the spots for a sub k and k. But I'm actually going to substitute in the value of a sub 3. It says that it's equal to 8. Let me just do one sign here. So -3 and -3. All right, algebra time. We need to reduce this and solve it for an expression, kind of like solving for slope-intercept form. So my brain wants to do this first, wants to distribute. Hopefully yours did too. This would be 8 minus 3n plus 9. And sequences are not written with the slope usually coming first. We write it with the initial value first. So I'm going to simplify the 17 in the front and have it be 17 minus 3n. And I know for slope-intercept form, we usually put the slope first. But for sequences, we flip that order. We put the initial value first and then the slope second, or the common difference in this case. Did we follow? Okay, cool. We're going to go on and we're going to use this to find a sub 12. Well, if I want to find a sub 12, it's telling me to plug what number in to my sequence? 12. Okay, easy. 3 times 12 is 36, so 17 minus 36, that's negative 19. So we would get that a sub 12 is equal to negative 19. We'd have a coordinate point in the sequence if we were plotting it, air quotes coordinate point, I mean it's a coordinate point, of 12 comma negative 19. Did we follow? Okay, so this is very similar to a question that would give you a point and a slope and ask you to write an equation. We did that. We wrote point slope, we solved it for slope intercept. I know that these are sequences, but I'm trying to connect it to things you know. Example 4 is going to take it one step back further. Example 4 says, let a sub n be an arithmetic sequence with a sub 2 equal to 7 and a sub 6 equal to 9. Did they give us a common difference? No. Can we use these 2 points, though, to find some sort of common difference? I'm going to use a different color. We totally can. It's just a little bit more work. We're going to, again, find an expression for a sub n, then use the expression to find a sub 24. So it's the same kind of question with different sort of information given to you. Now, again, I'm going to use this equation from the top of my page to write one equation for myself with 2 separate inputs, where both a sub n and a sub k are changed to one of the things I was given. We'll let a sub n be the red part. So we have a sub n equal to a sub k plus the common difference, which we do not know, open parentheses, n minus k. Well, n should be 2, and k should be 6. Did I lose anybody? Just like taking x's and y's and plugging them into point slope form, that's what we're doing here. Okay? Well, a sub 2 and a sub 6 have values. A sub 2 is actually 7, and a sub 6 is actually 9. So I can take those 2 numbers and plug them in. Do we follow that? Okay, well, at this point, look at your equation. How many variables do you have left? One variable, one equation, you can solve for it. 2 minus 6 is negative 4. I'm just simplifying here. So this is 7 equal to 9 plus, we'll do minus 4 times d, because 2 minus 6 is negative 4. Subtract 9 to both sides, that would end up being negative 2 equal to negative 4 times d. Divide by negative 4 on both sides. Negative divided by negative cancels. 2 divided by 4 is 1/2. So we get that d is equal to 1/2. That's awesome, but that's not what the final answer is. In fact, all we've done so far is find the common difference. We are now at the place where we started question number 3. Number 3 started with giving you a random point and a common difference. We now have 2 random points and a common difference. Just so I can make sure we understand, can you guys take it from here? So you're repeating the steps we did in example 3, but with these problems. A question I assume you're going to ask, does it matter if you use the red or the green point? No, you'll end up with the same answers. I'll use the red point if you want to use the one that I'm going to use when I go over it, just FYI. All right, so we're plugging in things we know. And again, yes, you could use the green point or the red point. It doesn't matter. When you reduce, they end up being the same. But we plug them into the original equation again and start simplifying. A sub n would be equal to 7 plus, I'm going to go ahead and do 2 things at once, 1/2 n minus 1. We combine our like terms, which is the constants in the front. This would be 6 plus 1/2 n. That is the equation for a sub n that it was asking for. But then it wanted us to turn around right away and use that function or that sequence to find a sub 24, which just means we are plugging 24 in as n, the 24th term in the sequence. Half of 24 is 12. 6 plus 12 is 18. So a sub 24 is equal to 18. Questions, comments, concerns? Yes. Okay. Let me see. Well, let's see. Okay, so that's a really good point to make because I think a couple of us did this. The purple part is the second question here. If you were to take the numbers 24 and a sub 24 and use them up here, meaning you'd say a sub 24 and then put a 24 here, you would end up reducing it down to 18. So that's not answering the question incorrectly. You've just missed a part. Since it did ask to find an expression for a sub n, we needed to write that simplified equation. But if it's only asking you to find a sub 24, you could straight up plug in 24 at this point and find a sub 24. That's totally fine, because that is an equation. Well, I guess this one, because that's where I substituted it in. But it is an equation if it doesn't tell you how you have to reduce it, but we needed to reduce it to look like this. Great question. Okay, example 5 says, several terms of the arithmetic sequence a sub n are shown above. Find an expression for a sub n and use the expression to find a sub 17. So literally the same kind of question. We're writing a sequence and then using the sequence. This time they didn't give us the common difference. They just gave us a bunch of points on a graph. Here's some things to notice. What is that? I think I heard somebody say B, the y-intercept. Cool, but this is a sequence. So instead of that, what do we call it? Initial value. So we're going to say a sub 0, which is our initial value, is going to be equal to 8. I know it's a sub 0 because it's on the x value of 0. So it's the 0 term in the sequence, the 0th term in the sequence. I can also find all the coordinates here and then do some math to figure out the common difference, or use our ability as pattern finders to find this common difference. If I go from 8 to 6, what did I do? If I go from 6 to 4, what did I do? And then 4 to 2, and then 2 to 0. Oh, look at that. What is the change every time? What is my common difference? -2. Awesome. Because we're looking at that common difference, or how they changed with adding and subtracting, we can find this common difference pretty quick. This time, because we found the initial value first, we don't have to use the version of the formula with the k's in it. We can use the slope-intercept, air quotes, slope-intercept version of this, where all you have to plug in is your common difference and your initial value. And check it out. We literally have those two things. We have our initial value and we have our common difference. So my equation gets much easier to write when I'm given that y-intercept, when I'm given the initial value. That means this is 8 minus 2n. Does that make sense? Why we did not have to use the longer version of the equation for the sequence? We were given the initial value, so we can use the shorter version. And then again, we want to find a sub 17. Wow, I keep picking the wrong colors here. A sub 17, so we would do a sub 17 is equal to 8 minus 2 times 17. 2 times 17 is 34, so 8 minus 34 is -26. We feeling okay on these kinds of questions? Yes, no, maybe so? So arithmetic sequences, when we've been using them, we've been using adding and subtracting because they look like linear equations. The next type of sequence we're going to talk about is called a geometric sequence. This is not going to use adding and subtracting to change. In fact, geometric sequences, they don't have common differences. They have what's called a common ratio. A common ratio or constant proportional change, meaning that we are going to find the common ratio not by adding and subtracting, but we're going to find that common ratio by taking two terms, g of k and dividing it by the term before it, g of k plus 1. Sorry, that should not be a plus 1. That should be a minus 1. Okay, so you did this with arithmetic sequences. To find the difference, you subtracted the second one minus the first one. In this case, we're not subtracting the second minus the first. We're dividing the second minus the first. We'll get to what that means in a second. Again, there are two formulas we can use here for our sequences. We have our one where we are provided with the initial value, g sub n equal to g sub 0 times r raised to the n power, or the version where you are not given the initial value, g sub n equal to g sub k times r to the n minus k. Again, very similarly, g sub 0 is still called our initial value or initial amount. You'll see that one a lot. R is our common ratio, and g sub k is the kth term in the sequence. So if they give you a random term in the sequence, you're putting it in the g sub k version, not the g sub 0 version. Now I know you can read the word in the next little box, but what do these equations kind of look like? When you have an exponent that is a x, they are called what kinds of functions? Exponential. So these are going to model like exponential functions, again, except that they are not continuous. They are still discrete, just like our arithmetic ones are, because we go from the whole numbers to the real numbers. We can't plug in negative numbers or fractions, so they're going to all be broken apart. Increasing geometric sequences increase by a larger amount each step, but the percentage increase always stays the same. Really meaning we are going to be multiplying or multiplying by a fraction, dividing, each time we get new numbers in these sequences. So for example, g sub n is equal to 8 times 1/2 raised to the n. We're going to graph this, but just like before, we want to have a table of our values, g and g sub n. N and g sub n. Now, just like arithmetic, we don't plug in fractions. We don't plug in negative numbers, so we're going to start at 0. This would be 8 times 1/2 raised to the 0 power. Ooh, let's remember some exponent rules. What is anything raised to the 0 power? 1. So this is 8 times 1, which is 8. I'll plot it in a second just so I don't have to keep moving my screen side to side. If we plug in 1, 8 times 1/2 raised to the first power. Again, PEMDAS tells me to do those exponents first. What is 1/2 raised to the first power? 1/2. So this is like 8 divided by 2, which is 4. Check. If we plug in a 2, and don't answer right away, I want you to think, what is 1/2 raised to the second power? 1/4. Here's why, just as a little extra. When you are raising a fraction to a power, you can essentially, I don't want to use the word distribute because it's not distribution, but with the arrows it kind of looks like it. You can square the top and square the bottom separately, which would be 1 squared 1, 2 squared 4. So 1/2 raised to the second power is actually like doing 8, wrong color, 8 divided by 4, because it's 8 times a fourth, which is 2. We'll just do one more for good measure. 8 times 1/2 raised to the third power. What would 1/2 raised to the third power be? Too much. 1/8. So this is like 8 divided by 8, which is 1. What do you notice about all of these outputs? If we go from 8 to 4 to 2 to 1, what has happened every time? We've divided by 2 because our common ratio is 1/2. That makes a lot of sense. So we're seeing that these functions don't change by adding and subtracting. They change by multiplying and dividing. So if I plot these points, here's 0, 8, 1, 4. Half of that is 2. Half of that is 1. If we were to keep going, what would be the next number? One half. And then if we kept going, the next one would be 1/4. Okay, I wanted to do that because now you can see the shape. That looks like an exponential function, an exponential decay function. Again, resist the urge to connect the dots because they do not connect. They are discrete. Okay, so when we know we're working with geometric functions, we're adding, not adding and subtracting is literally what I was going to say we aren't doing, multiplying and dividing. So if we go look at these sequences to determine if they're geometric, we again just need some values, n and s sub n, to see what's happening with those outputs. If I were to plug in 0 to s sub n, part A, there'd be 3 times 0 squared, which is 0. If I plugged in 1, 3 times 1 squared is 1, so 3 times 1 is 3. If I plug in 2, 2 squared is 4. 3 times 4 is 12. If I plug in 3, 3 squared is 9. 9 times 3 is 27. What is the change using multiplication or division to go from 0 to 3? Is that even possible at all? No, because you'd be multiplying by 0, right? So that's not even possible. Right there, we already know that this is not going to be geometric. Okay, it's not going to be geometric because we can't even do the first term like that. So this is not geometric. I'll do part B with you just because it's a little bit different. It has an n minus 1 in the top, which makes it look weird, but it's just the same. So again, we have n and we have s sub n. If we plug in 0, this is like 4 times 2 raised to the 0 minus 1 power. What's 0 minus 1? Negative 1. What's 2 to the negative 1 power? Chris. Ooh, did we forget that one? That's okay, you can say I don't remember. 2 to the negative 1 power is just like flipping this over to 1/2. Yeah. To positive 1 power, but like we don't write the ones. Okay, yeah. Okay, so this is like saying 4 times 1/2. What is 4 times 1/2? 2. Okay, great. So my first term here is 2. If we plugged in a 1, 4 times 2 to the 1 minus 1. What's 1 minus 1?
0.
What's anything to the 0 power? 1. Which means that this is 4. Because 4 times 1 is 4. We plug in 2. This is 4 times 2 to the 2 minus 1. What's 2 minus 1? 1. 2 to the 1 power is 2. So 4 times 2 is 8. We'll do one more for good measure. 4 times 2 to the 3 minus 1. What's 3 minus 1? 2 squared is 4, and then 4 times 4 is? Okay, look at these outputs. What number do I have to multiply by to go from 2 to 4? 2. If you couldn't tell, because sometimes the common difference will be some sort of fraction, the way you figure this out is you take the second term divided by the first term. The second term divided by the first term. The second term divided by the first term. This one's easy to see because it's 2, but again, if it was some sort of fraction that's hard to see, you take the second term divided by the first term. Second term, well, third by second, fourth by third. Does that make sense? Okay, but we see that this number is the same every single time, and since this number is consistently being multiplied by 2, that would make this a geometric sequence, and the common ratio would be that number 2. And this makes sense. Because again, if you think about what you knew at some point about exponential functions, the common ratio is the number in the parentheses. That's why these numbers are both the same. I'll leave C and D for you. Just quickly identify if they are geometric, and if they are, find me the common ratio. If you're stuck because the numbers don't look like a pattern to you right away, do the second divided by the first, third divided by the second, fourth divided by the third to see if that is consistently the same ratio. Okay, if we were going to look at the part C, the first sequence written there, and again, I don't particularly see a pattern when I just look at it, but sometimes it's deceiving. So we go ahead and do the first term, sorry, the second term divided by the first would give me 3. So that's the change here. I do the third term divided by the second. Well, that's just 2/3. That's the change between these two. Are those the same number? All right, immediately I know it's not following a consistent pattern. I could do more if I wanted to guarantee it for myself, but I know right away that this is not geometric. Because even just the first 2 terms don't change by the same ratio. I'd have to multiply by different numbers to get that to happen. But if we look at D, again, maybe your eyes don't necessarily see the pattern. You can kind of see the numbers getting smaller, but they change from sign to sign, which is concerning. So we go ahead and do that same pattern. Between these two, we would do -8 divided by 16, which is -1/2. Between these two, we'd do 4 divided by -8. What does that also reduce to? -1/2. Then we do -2 divided by 4. Oh, look, that's still -1/2. And then we do 1 divided by -2. That's -1/2. Since all of those numbers are the same ratio, this actually is a geometric sequence. And the common ratio is the number -1/2. Did we see that? Now it's concerning. I think we've probably never seen one that oscillates between positive and negative before. Kind of weird, but definitely works for a sequence. All right, number 7. Let G sub n be a geometric sequence with G sub 1 equal to 12 and R equal to 2. Find an expression for G sub n and use the expression to find G sub 4. Sounds really familiar, but this time we're doing it not with arithmetic, but with geometric sequences. Okay? We are given essentially a coordinate point and your common ratio, which means we're going to want to fill in the equation G sub n equal to G sub k times R to the n minus k power, because we weren't given the initial value. No big deal. We know that G sub k and k are the initial things I was given, the coordinate point I was given, and R is my common ratio. We can plug all those things in. That means that this would be G sub n equal to G sub k, that's 12, times the common ratio, which is 2, to the n minus k, which k is 1. For these kinds of functions, we're not going to simplify them just yet. We haven't really been through the algebra required to rewrite exponential functions, so we're actually going to stop here and not try to get it into its like typical form, I guess I should say, with the initial value showing. So that's an okay way to stop. But because, again, we're wanting to use this equation to find G sub 4, all we would need to do is take the number 4 and plug it in where the n goes. Okay, what is 4 minus 1? Yeah, don't overthink it. 3, okay. What is 2 to the third power? Don't say 6. 8, I heard it. So then we're doing 12 times 8. So 2 times 8 is 16, carry the 1. 1 times 8 is 8, plus 1 is 9. That's 96. You see how it's very similar to when we did this with arithmetic? I want to leave example 8 for you to try right now. It's very much like the arithmetic version we had where we were given the graph, so you have an example to see. But I want you to write the geometric sequence shown and then find G sub 10. I will say you probably will need to use your calculator to do G sub 10. I did. Not gonna lie. Okay, so we should be filling in the version with the initial value showing. And the reason I know we should be filling in the version with the initial value showing is because I can straight up see the initial value. What is the initial value here? 8. So a sub 0 is equal to 8. My y-intercept, my initial value, my initial amount is 8. I guess this should be a G, not an A. Okay, now I just need to know how this pattern is changing. So if we look from 8 to 4, not using addition and subtraction this time, but using multiplication or division, which is multiplying by a fraction, what's happening here? Times a half. Thank you for saying times a half. And if we go from 4 to 2, again, times a half. And then 2 to 1, times a half. I see a consistent pattern here, which means I know that my common ratio is 1/2. So we could write this equation as G sub n equal to 8 times 1/2 raised to the n power. It's actually the exact pattern we had in the table up above. But then we go on and it asks us to find G sub 10. This is the one that I'm assuming we might need to use a calculator for because we're doing 8 times 1/2 raised to the 10th power. Oof, what is 1/2 to the 10th power? Let me rephrase. What is 2 to the 10th power? It's a big number. 1024. So we're doing 8 divided by 1024, which would reduce to 1/128. But of course, if you had a calculator, you could just go from here to here. I just showed my work. Last comments, questions, or concerns. Here's some things I want to tell you about these kinds of sequences. The questions are all written very similarly. You need to make sure when you're looking at questions for sequences, you're understanding what kind of sequence they're giving you. They should explicitly tell you what kind of sequence it is unless they give you the outputs and you're figuring it out. So it will say a geometric sequence does blah, blah, blah. An arithmetic sequence does blah, blah, blah. Okay, you just make sure you look for what type of function you're using so you know which formulas to use. Second thing, you are not provided with a formula chart in this class on the test. So these formulas are going to be something we maybe need to put in our brain for future use. Okay? Potentially there's like going to be a quiz maybe with like a place where you write them down. I don't know. Maybe that would happen. So I would make sure that we have these formulas that are on both pages memorized. Just some food for thought.